Okay, so now we're going to start talking about Hayworth structures of carbohydrates. I'm going to be dead honest. When I first learned this, I learned it incorrectly as Hawthorne, and I apologize if I make that mistake throughout this lecture. It is Hayworth. It got stuck in my brain the wrong way many years back, and I still make that mistake today. I'll try to do my best. But yes, the Hayworth structures of carbohydrates, these are these ring type structures that we've seen. Okay, so our goal is going to be to go from those Fisher projections, those long stick type of structures, to the Hayworth projections, to the Hayworth structures. Okay, and real quick, I'll just say beforehand, why do we need to do this? This is actually the dominant form that sugars exist in your body. They actually exist more as these rings than they do as long chains. And these are the structures that your body's metabolism deals with. So when it goes to link sugars together to make starches or disaccharides, polysaccharides, it does so with the ring form. So that's why these are really important. Up until now, we've been talking about them in those long stretched out structures, which we call the Fisher projections. We're going to now almost exclusively switch to these ring structures, these Hawthorne structures, okay? Step one is how do we get from one to the other, right? Because that's going to be the real deal here. Luckily, it's not too bad, but it is its own little thing. Okay, so first of all, given a open chain form of glucose, for example, this would be D-glucose. Why is it D-glucose? Because we got this OH group on the right. First thing we're going to do is lay these Fisher structures down on their side. So we're going to go ahead and rotate them clockwise by 90 degrees. Okay. Importantly, everything that was on the right is now on the bottom. And everything that was on the left is now on the top. And all of our carbons still match, right? I mean, again, one of the differentiating factors with carbohydrates are the position of those hydroxide groups and the hydrogens along that chain. So those need to match, right? So on carbon 2, there was a hydrogen pointed to the left. So on carbon 2, there should be a hydrogen pointed up. On carbon 3, there was a hydroxyl group on the left. So there should be a hydroxyl group on the right, et cetera, right? So not only do you have to lay these things down on their side, you want to do so carefully and make sure that your groups are still matched to what they were before. All right, so step one, turn it 90 degrees. Okay, so again, step one, we're going to turn this structure 90 degrees. Clockwise 90 degrees. Okay. Now what we're going to want to do is, so now from here, what you're going to do is draw a hexagon. Okay. And actually this bond isn't there yet, because how we're going to number it is to make sure that your front two carbons are carbons 2 and 3. Okay, so carbons 2 and 3 should form the base of your hexagon. And now you're going to go through and make sure that when you insert your OH groups and hydrogens, that they line up the correct way. So this carbon is, let me actually use red to number 1, 2, 3, 4, 5, 6. So carbon 1, this is the one that has that aldehyde group. Carbon 2, in my Fisher projection, I set down on the side, the hydrogen is pointed down. That means that in my hexagon, I'm sorry, the hydroxyl group is pointed down, which means that in my hexagon, the hydroxyl group is going to be pointed down. On carbon 3, in my Fisher projection that's on the side, the hydroxyl group is pointed up. That means that on carbon 3, I want my hydroxyl group pointed up. On carbon 4, on carbons 4 and 5, the hydroxyl groups are pointed down. So on 4, and 5, my hydroxyl groups are pointed down. And then carbon 6 is that CH2OH. Okay, so notice that the structure, the hydroxyl groups that are pointed down in my Fisher projection are pointed down in my sugar, in my Hawthorne structure. The ones that are pointed up in my Fisher projection that is laid down on its side are going to be pointed up in my Hawthorne structure. Okay, so step 2, draw that hexagon and make sure that your front carbons are carbons 2 and 3, and then fill in those hydroxyl groups so that everything matches. Okay, so now that takes us to here, right? Line everything up. We have our hydroxyl groups pointed in the right directions, all that good stuff, right? Now we're going to rotate that that carbon 5. We're going to switch the position of all those groups. So that means that the hydrogen is going to come down and replace that OH group. The hydroxyl group is going to come up and replace the CH2OH, and CH2OH is going to go to the top there. Okay. All right, give me a second to clean up. We're not here yet. So this is what we should get once we rotate those groups. So again, if I'm just going to sort of color code, this group got rotated to over here. This one rotated to the top, and the hydrogen rotated to the bottom. Okay. Remember, we're allowed to do that for our Fisher projections. As long as we're rotating 3 of those groups, we keep the structure the same. So we haven't like redrawn our molecule and made the enantiomer or anything like that. This is the same molecule. We've just rotated those 3 groups. Okay. And now the OH group of carbon 5 is going to form a new bond with carbon 1. All right, so let's see what that looks like. This will close our ring. Okay. Actually, let's talk about what this is in a second. Let's just make note here of what's going on. Again, this carbon here that was the OH group on carbon 5, that becomes the oxygen that's actually like a part of this ring, right? This is a 6-membered ring. 5 of those atoms are carbon. The other one is oxygen. This, remember what we call carbonyl carbons in when we're talking about sugars. This is our anomeric carbon. That's carbon 1. Or even though it's not a carbonyl carbon anymore, it's still the anomeric carbon when you're in your closed ring structure. So that's part of why the name is part of where the designation comes from. Okay. And then what was formerly your carbonyl oxygen is now an OH group, is now an alcohol. Okay, so take a second to convince yourself that this makes sense as to where those atoms all went. Okay, now for that anomeric carbon, and specifically the hydroxyl group on that anomeric carbon, what I've colored here in purple, you could have either drawn it pointed up or pointed down. There's no way to determine beforehand which way it would be. All right, so this is another set of isomers that are formed as this ring is closing, right? So you're going from the open chain to the closed chain form. That anomeric carbon, the OH group on that, it can be in one of 2 directions. If it's pointed down, that's what we call the alpha isomer. Okay, or this ring could have closed where that anomeric carbon, the OH group on that anomeric carbon, is pointed up, and that would be called the beta isomer. Okay, so again, these are 2 perfectly acceptable ways of drawing the closed ring form of glucose. They are in equilibrium with one another. We call it the alpha isomer and the beta isomer. Alpha means OH on anomeric is down. Beta means that the OH on anomeric is up. Okay, so you have this glucose that's in its open chain form. It goes to this closed chain form. It could produce either the alpha or the beta isomer. Okay, at this point, the only thing that's important is that we can look at a closed chain form of a sugar and distinguish whether or not it's the alpha or the beta isomer. So again, we're going to find that anomeric carbon and figure out which direction that hydroxyl group is pointed. This was a hard one for me to remember. Alpha is down, beta is up. I'm not saying that this is going to work for everybody, but the way that I sort of had it in my brain is that down comes before up alphabetically. D is before U alphabetically, just like alpha is before beta alphabetically. I'm not saying that will help, but I was having trouble remembering it, and that's sort of a little device that I created to help my memory be able to distinguish it a little bit easier. So hopefully that helps. If not, you have to come up with your own little trick in order to remember that the alpha means that OH group on the anomeric carbon is pointed down. Beta means that the OH group on the anomeric carbon is pointed up. Okay, and again, so really we have this, so this is the open chain form of glucose. And what's being shown here is that these two forms, the alpha and the beta isomers, are all in equilibrium with one another. So it's the alpha form is in equilibrium with the open chain, is in equilibrium with the beta form, and vice versa. Okay, and it turns out that the beta form is a little bit more favored. For our purposes, we can kind of imagine, whoa, you can kind of think of it, I think that's specific to glucose as opposed to for all sugars. We can think of these alpha and beta isomers as being present in like a 50-50 distribution. Importantly though, the open chain form is the least likely, right? So there's only a trace amounts of glucose in your body that's actually floating around in the open chain form. It's constantly swapping back and forth between alpha and beta. But if you were to like shrink down and grab a glucose molecule, vast majority of the time you would find it in those cyclic forms, not in the open chain form, right? So we sort of started talking about carbohydrates in the open chain form. We learned a little bit about how to classify them in the open chain form, but it turns out that when they're floating around in our body, they're floating around in these closed chain forms. Okay, galactose, same deal. You're gonna start out with a different, right? So here's my constants page. We did this procedure for glucose where we took it, we rotated it 90 degrees, and then we went about drawing our Hayworth structure. We could do the same thing for galactose, right? We can do the same thing for fructose. We can do the same thing for any sugar that I would give you. Actually, it has to be like a hexose. But nonetheless, we could do it for a lot of different sugars that we were given. All about sort of matching where those OH groups are pointed either up or down. Just like glucose, there's an alpha and a beta isomer. And I should have kind of hidden this so we could get practice figuring out which is which. But let's look at these two here. If I'm going to determine whether or not it's the alpha or the beta isomer, I'm going to look for the anomeric carbon and look at which direction that OH group is. If the OH group is pointed down, that's the alpha isomer. And if the OH group on the anomeric carbon is pointed up, that's the beta isomer. Okay, you'll see, you know, just like we saw with the in the Fisher projections of glucose versus galactose, the big difference is what's happening on carbon 4. In galactose, the hydroxyl group is pointed up. If we look at glucose on carbon 4, that hydroxyl group is pointed down, right? So that was really the only difference between glucose and galactose. Fructose. So fructose is a little bit different than the other two because it's a hexose, but it's a ketohexose, right? So that means that when we fold it up into our little, you know, we've taken our Fisher projection, folded it down on its side, the anomeric carbon is actually carbon 2, not carbon 1, which means that we're going to have a 1, 2, 3, 4, 5 membered ring not a 6-membered ring. So the Hayworth structure of fructose is a 5-membered ring. And again, that's because your anomeric carbon is actually carbon 2, not carbon 1. Right? Just like all the other sugars, you have an alpha and a beta isomer of fructose. How are we going to figure that out? We're going to find the anomeric carbon, figure out which way the hydroxyl group is pointed. So notice that this time on the other side is not just a hydrogen, it's a CH2OH. Nonetheless, we're still focused only on the hydroxyl group of that anomeric carbon and whether it's pointed down or up. If it's pointed down, that's alpha fructose, and if it's pointed up, that's beta fructose. Okay, but now your bond again is formed between that last chiral hydroxyl group, so on the hydroxyl group that's on carbon 5, and your anomeric carbon. In the case of fructose, since it's a ketohexose, you'll produce a 5-membered ring. Okay, so here's a good example. I actually did this a little bit different than what was in the study guide, specifically so we can practice given a sugar that we've never seen before. Okay, so this is mannose. As you can see, the only difference is the positions of the hydroxyl groups and the hydrogens on all those chiral carbons. Okay, so step 1, we're going to flip it on its side. Here we have our aldehyde group. Make sure I have the correct number of bonds. 1, 2, 3, 4. And then I'll put in my achiral carbon at the end there, the CH2OH. Right? And then I want to make sure that on carbons, so this is 1, 2, 3, 4, and 5, everything is positioned in the correct way. So these were all on the left. Nope, those were all on the right, which means that they should be on the bottom. Okay, so on carbon 2, I'm actually going to get rid of that. We have our hydrogen, hydrogen, OH, OH. And then on the right, or yeah, what was formerly on the left is now on top. So we have OH, OH, H, H. Okay, so that was step 1. Step 2 is we're going to draw our hexagon. We're going to make sure, and the whole shtick of how we're drawing our hexagon is to make sure that carbons 2 and 3 are out front. Okay, so carbon 1, this is the aldehyde. On carbon 2, the OH group should be pointed up. On carbon 3, OH group is up. Carbon 4, OH group is down. Carbon 5, OH group is down. And then on carbon 6, that's that CH2OH. Okay, I'm going to specifically draw in that hydrogen there, because now we're going to have to, for our last step, our next step is going to be to rotate. Up, up, down. Now a hydrogen should be here. The OH group is there, and this is the CH2OH. Okay, and now the last step is going to be to draw a bond between this oxygen and the anomeric carbon. For the sake of saving time, I'm just going to sort of erase to make new bonds. So that would go there. And then I can have either the alpha isomer, where it's pointed down, or I can have the beta isomer, where it's pointed up. but these would be the alpha and beta isomers of D-mannose in that closed chain form.